Beneath the complexities of everyday life, the rules of our universe seem reassuringly simple. This solid bridge supports my weight. The water flowing underneath always goes downhill. And when I throw this stone, it always flies through the air following a predictable path. But as scientists peered deep into the tiny building blocks of matter, all such certainty vanished. They found the weird world of quantum mechanics. Deep down inside everything we see around us, we found a universe completely unlike our own. To paraphrase one of the founders of quantum mechanics, everything we call real is made up of things that cannot be themselves regarded as real. Around 100 years ago, some of the world's greatest scientists began a journey down the rabbit hole into the strange and the bizarre. They found that in the realm of the very small, things could be in two places at once. That their fates are dictated by chance. And that reality itself defies all common sense. And at stake, that everything we thought we knew about the world might turn out to be completely wrong. The story of our descent into scientific madness begins with a most unlikely object. Berlin, 1890. Germany is a new country, recently unified and hungry to industrialize. In this newly unified Germany, a number of new engineering companies were founded. They had spent millions buying the European patent for Edison's new invention, the light bulb. The light bulb was the epitome of modern technology, a great optimistic symbol of progress. Engineering companies quickly realized there were fortunes to be made building streetlights for the new German Empire. But what they didn't realize was that they would also unleash a scientific revolution. Strangely enough, this humble object is responsible for the birth of the most important theory in the whole of science, quantum mechanics, a theory that I've spent my life studying. And that's because back in 1900, the light bulb presented a rather strange problem. Engineers knew that if you heated the filament with electricity, it glowed. The physics that underpinned this, though, was completely unknown. But something as basic as the relationship between the temperature of the filament and the color of light it produces was still a complete mystery. A mystery they were obviously keen to solve. And with the help of the new German state, they saw how to steal a march on their competitors. In 1887, the German government invested millions in a new technical research institute here in Berlin, the Physikalisch-Technische Reichsanstalt, or PTR. Then, in 1900, they enlisted a bright, if somewhat straight-laced scientist to help work here. His name was Max Planck. Planck took on a deceptively simple problem: why the color of the light changes as the filament gets hotter. To get a sense of the puzzle facing Planck, I'm going to ride this bicycle with an old-fashioned lamp powered by an old-fashioned dynamo. Obviously, the faster I go, the brighter the light. The more I pedal, the more electricity the dynamo produces, the hotter the filament in the lamp, and the brighter the light. But the light the bulb makes isn't just getting brighter. it's changing color too. As I speed up, the color shifts from red to orange to yellow.
Right, now I'm going to really belt it.
Now the bulb's filament is getting even hotter, but although it certainly gets brighter, the color seems to stay the same, yellow-white. Why doesn't the light get any bluer? To investigate, Planck and his colleagues built this, a black body radiator. It's a special tube they could heat to a very precise temperature and a way to measure the color or frequency of the light it produced. Nowadays, over 100 years later, the PTR still do exactly this kind of measurement, just much more accurately.
The temperature inside here is 841 degrees centigrade. I can feel the heat coming off, and it's glowing with a lovely orangey red color.
It's about the same color as my bike light when I'm cycling slowly. But I want to see something hotter still.
The temperature inside here is about 2,000 degrees centigrade. And it's glowing with a much brighter, whiter colored light. To produce light of this intensity and color requires a power of about 40 kilowatts. Now, that's equivalent to about 400 me's on a bike cycling very fast, or the combined output of the entire Tour de France.
Although the light is whiter, it's red-white. There's very little blue. Why is blue so much harder to make than red? And further up the spectrum, beyond blue, the so-called ultraviolet is hardly produced at all, even when we look at things as hot as the sun.
Even the sun, at a temperature of 5,500 degrees centigrade, produces mostly white visible light and makes remarkably little ultraviolet light given how hot it is. Why is this? Why is ultraviolet light so hard to make? This remarkable failure of common sense so perplexed scientists of the late 19th century that they gave it a very dramatic name. They called it the ultraviolet catastrophe.
Planck took a crucial first step to solving this. He found the precise mathematical link between the color of light, its frequency, and its energy. But he didn't understand the connection. However, it was another weird anomaly that would really put the cat amongst the pigeons.
In the late 19th century, scientists were studying the then newly discovered radio waves and how they were transmitted. And to do that, they were building experimental rigs very similar to this one. Basically, by spinning this disk, they could generate huge voltages that caused sparks to jump across the gap between the two metal spheres. But in doing so, they discovered something very unexpected to do with light. They found that by shining a powerful light source on the spheres, they could make the sparks jump across more easily. This suggested a mysterious and unexplained connection between light and electricity. To understand what was happening, scientists used this. It's called a gold leaf electroscope. It's basically a more sensitive version of the spark gap apparatus. Now, first of all, I have to charge it up. What I'm doing is adding an excess of electrons that are pushing the two gold leaves apart. Now, first I take red light and shine it on the metal surface, and nothing happens. Even if I increase the brightness of the light, still the gold leaves aren't affected.
Now I'll try this special blue light, rich in ultraviolet.
Immediately, the gold leaves collapse.
light can clearly remove static electric charge from the leaves. It can somehow knock out the electrons I added to them. But why is ultraviolet light so much better at doing this than red light? This new puzzle became known as the photoelectric effect. The ultraviolet catastrophe and the photoelectric effect were big problems for physicists, because neither could be understood using the best science of the time. The science that said quite unequivocally that light was a wave. All around us, we see light behaving in a perfectly common sense, wavy way. Look at the shadow of my hand. It's fuzzy around the edges. We understand this as the light hitting the sides of my hand and bending and smearing out slightly, just like water waves around an obstruction. Perfectly common sense, wave-like behavior. And here's something else, something rather beautiful. Look at these soap bubbles. Shine a light on them and gorgeous colored patterns emerge from nowhere. And this was easily explained if you accept that light was a wave, reflecting off the outer and inner layers of the thin soap film and breaking up into the colors of the rainbow. Rather like ripples on the surface of water, light was simply ripples of energy spreading through space. And this was as firmly accepted as the fact that the Earth was round. But although this wave theory worked perfectly well for shadows and bubbles, when it came to the ultraviolet catastrophe and the photoelectric effect, the wheels started coming off. The problem was this: how could light do this? To truly grasp how absurd this phenomenon was, it might be useful to consider how waves in water behave. This is the wave tank at the RNLI's headquarters in Dorset. It's used to train lifeboat teams to deal with a range of different kinds of water waves. First, small waves, just 30 centimeters high. These waves don't have much energy, hardly enough energy to knock this top can off the other. But when the waves grow to over 1.5 meters, it's a very different proposition. And they're really throwing me about. There's no way I can keep this can balanced on the top. It's clear what water waves are telling us. Bigger, more intense waves have more power. They easily knock me and the cans around. So if light was a wave, more intensity should knock out more electrons. But that's not what happened. Remember, no matter how intense the red light was, it still didn't budge electrons from the metal. But weirdly, weak ultraviolet worked within seconds. So thinking of light as a wave just wasn't adding up. To resolve this, someone needed to think the unthinkable. And in 1905, someone did. You may well have heard of him. His name was Albert Einstein. This is the Achenhold-Sternwarte Observatory in Berlin. Perched on top is a strange, huge iron and steel construction. But it's not a gun. It's actually a telescope. Built in 1896, the telescope was one of the largest of its kind in the world and made the observatory the go-to place to engage and astound the public in new science. Albert Einstein gave a very famous public lecture here on his theory of relativity, which is, of course, what he's most famous for. But it's not the work that won him the Nobel Prize. In 1905, he'd also come up with a new theory to explain the photoelectric effect. And what he suggested was revolutionary and even heretical.
He argued that we have to forget all about the idea that light is a wave and think of it instead as a stream of tiny bullet-like particles. The term he used to describe a particle of light was a quantum.
To Einstein, a quantum was a tiny lump of energy. And although in 1905 the word wasn't new, the idea that light could be a quantum seemed crazy. And yet, following Einstein's heretical line of thought to its logical conclusion, solved all the problems with light at a single stroke.
I'll try to explain how this helps using a rough analogy. Of course, like all analogies, it's far from perfect, but hopefully it'll give you a sense of the physics to help you understand why thinking of light as a stream of particles solves the mystery of the photoelectric effect. In this analogy, these red balls represent Einstein's light quanta.
And those cans over there are the electricity held in the metal.
Now, in the original experiment, they made electricity flow from the surface of the metal by shining light on it. In my analogy, I'm going to try and knock those tin cans over using these red balls.
Absolutely no effect. That's just like red light. According to Einstein, each particle of red light carries very little energy because red light has a low frequency. So even a very bright red light with many red light particles can't dislodge any electrons from the metal plate, just like the red balls.
Now I'm going to use heavier balls, like these blue golf balls, and I'm going to try and knock off the tin cans with these.
They're like the ultraviolet light in the experiment. Now, each individual light particle carries more energy because ultraviolet light is higher frequency. Just a few of them, like a dim ultraviolet light, are enough to knock the electrons out of the metal plate and collapse the gold leaf.
So Einstein's idea that light is made up of tiny particles or quanta is a wonderful explanation of the photoelectric effect. I remember when I first learnt about this, being blown away by its sheer elegance and simplicity.
But what's more, Einstein's nifty idea also helped solve Planck's mystery of the light bulb. There was more red than ultraviolet because ultraviolet quanta took so much more energy to make, about 100 times more energy. No wonder there are so few of them.
That moment at the beginning of the 20th century signaled a genuine revolution because it demonstrated that the kind of physical science that people were doing right back to Newton and Laplace and people like that, that you needed a completely new approach. Physics has never recovered from that moment in the sense that it's built on that moment. That's where modern physics really began.
But Einstein's theory also left physicists with a dizzying paradox, defying all common sense. Light was definitely a wave, which explained shadows and bubbles. And now it was definitely a particle too, Einstein's quanta, explaining the photoelectric effect and the ultraviolet catastrophe.
Then, just a few years after Einstein's brilliant, crazy idea, the paradox got a lot deeper and a whole lot weirder.
because what seemed to be a curious mystery about light was about to become a battleground about the nature of reality itself.